right, separation of variables leads to a class of what we can call eigenvalue problems, right? The eigenvalue sort of gives you the rate at which the time coefficients decay. The eigenfunctions are going to be your Fourier modes that allow you to decompose your initial condition, okay? In general, they look like the following, right? For a large class of linear let's say second order PD, okay? And this is what's called the Sturm-Liouville problem, okay? And I'll just write this down. But in general, we can write our eigenvalue problem as some linear but possibly variable coefficient second order differential equation where x lies on some bounded domain, right? P is going to be greater than 0 for x is in A to B, okay? And we're going to have some linear and necessarily homogeneous boundary conditions at x equals A, B, okay? So remember that if we have inhomogeneities there, we ignore them when we solve for our Fourier coefficients, and we cook those basically into the initial value problem for our time-dependent coefficients. And then the limits will be right, but we'll still have you know, things that vanish according to the boundary conditions at the boundaries, right? And note, right, you can check this, right? The case P equals 1, right? Q equals 0, and R equals 1 corresponds to our previous problems, okay? All right. So the next step, right, is to really move beyond just the heat equation and discuss this general Sturm-Liouville problem, right? Which should apply to, you know, the wave equation or variable coefficient heat or wave equations, potentially with different kinds of boundary conditions, mixed boundary conditions, Robin, Neumann boundary conditions, periodic boundary conditions. And so we really want to dig into the theory of when this particular problem, or what we can say about this particular problem as far as the types of eigen solutions that it will produce. What we'd like for solving PDEs, right, because ultimately we're interested in solving PDEs, is for these eigenvalue problems to generate a complete orthogonal set such that we can satisfy our initial condition or conditions to our PDE, right? And once we know that we can do that, then we have a broad class of problems that we can apply separation of variables to. As you saw before, and you'll see on your homework, you can't always necessarily solve these eigenvalue problems by hand, but you can usually use root finding or something like that in order to get the eigenvalues and the corresponding eigenfunctions, okay? And that opens up the door to a lot of what are called spectral methods for solving PDEs, because it says that I can really decompose the solutions, the initial conditions, even the operators themselves according to these eigenfunctions. And it's powerful both for, you know, analysis of PDEs, but also it's turned into a lot of much faster and very accurate spectral methods for solving PDEs numerically. We're going through so much into that. That's more on the numerics and numerical PDEs type courses that we have. But that gives you some of a glimpse of the applicability of studying Sturm-Liouville theory. Okay, so we'll dig into that more on Monday. You should have all the tools you need now to solve your homework problem. So see you on Friday or you know, thereafter, depending on when you're watching this video.